Welcome to the implementation part of our sorting video, TLA plus specification. So we're going to dive right in. If you haven't watched the introduction to this video series yet, I encourage you to do so. Otherwise, let's get started. So this is the implementation piece. So we're going to start with bubble sort. And we're going to specify bubble sort to sort a collection of integers. And we're going to use a dialect within the TLA plus ecosystem called pluscal. And the pluscal dialect is a different style, if you will, and it tends to be particularly good at specifying sequential algorithms. So while TLA plus is great at kind of systems, pluscal can do that too. TLA plus can do sequential systems. Pluscal just makes it a little bit easier. So it's another tool in our toolbox. So let's start with our libraries. We're going to need sequences. We're going to need sequences, C-Q-U-E-N-C-E-S, integers, and then we're going to need TLC itself. Okay. We're going to define a constant, so the size of the array that we want to sort. We're going to make that a modeling constant. We're just going to call that size n. And then we're going to make an assumption. So the person that's consuming this module, the specification, they might ask, well, what is n? Remember, TLA plus is untyped. So we need to constrain it or define. I expect n to have some property or some relationship. Remember, n could be a string for all intents and purposes. So we're going to define an assumption that we're placing on top of n. So non-empty array. So this is kind of like executable documentation. Empty array. It's defined as n is within the set of natural numbers, and n is greater than 1. There we go. So now someone consuming the specification can say, oh, okay, I can pick n to be meaningful. And as you'll see later, we're going to do that somewhat odd thing of redefining what nat is to keep our model defined for what we care about at the moment. And this is how pluscal begins. It begins with a comment, bubble sort, and done. Okay, and when we save, we're going to get this, it's going to start generating or transpiling the pluscal into TLA plus. We're going to have some variables. A is going to be in 1 to n, which maps the natural numbers. So generate an input A of 1 to size n of the collection of natural numbers. So this is going to sort all the natural numbers of size 1 to n. A0 is equal to A. This is going to be helpful for the refinement step later, and then where we correlate the implementation to its interface. And that's what refinement really does. It lets you define the interface and then correlate it to an implementation, or you define the implementation first and you correlate it to the interface. That's the essence of refinement, but TLA plus lets you check it. 1, j equals 1, and total steps equals 1. Halil Wayne in the TLA plus community calls this a ghost variable. So this isn't essential for the algorithm, but we're going to try and check the computational complexity of bubble sort. It's just going to help us bound the model a little bit, make sure, help us check for errors. And total steps, we're going to update the steps incrementally to help us do that. Okay. Pluscal is a braced language. There is another syntax. I think it's called the P syntax for the Pascal style syntax. I use this one as the one I'm comfortable with. The beautiful thing is that TLA plus gives you these options, it gives you these sharp tools, and then it lets you apply them how you need. While I is less than n, we're going to do stuff. And I have automated translation turned on, so you can translate automatically. If you don't want to translate automatically, you can hit the translate and on demand. Okay, j equals I plus 1, and then while, what is this error upset about? Variables a. Okay, we're just going to keep going a little bit. J is greater than 1, and a j minus 1 is greater than a to j. Now, while a represents this set, when we're running the algorithm, it is one and only one instance of that set. So we're going to run it over a whole bunch of different values for a. Okay. All right. J. A j minus 1 a j. This does not mean or. This means do this step and this step simultaneously. So it's going to let us do a swap without a temporary variable, is what we're doing here. But catch yourself if you're coming from a programming language where this is a logical operator. It is not a logical operator in PlusCal. It means do the left side and the right side simultaneously. Okay, so that's just your swap operation, and it happens simultaneously because of we have that, so we don't need our temporary variable that we usually do when we implement swap. Okay, j minus 1. And then this is where we're going to update our ghost variable. This is one step worth of work. Total steps plus 1. Okay, looks good. We're going to put our semicolon there. Close that. We're going to put our semicolon there. Close that one. Okay, and then we're going to do I equals I plus 1, and total steps plus 1. Okay, and this is the bubble sort algorithm, straightforwardly implemented, except for we have that weird simultaneous step, and then we're also tracking total steps. So I'm going to fix this compiler error. Just a moment. Oh, see, it's just that guy. Okay. And translation's complete. So once you have I'm going to put that syntax error back in. That's where it failed. Fix our syntax error, and it translates our variables. And you can see that this is just a translation of this. So let's take this simultaneous variable away, and we can see how this behavior here is going to change. So this is that simultaneous operation in raw TLA plus. And if we remove it, oh, a semicolon. If we remove it, we can see that it does one step, and then the other step is going to be over here. So now there is two independent steps that this happens. And what that means in TLC, when we run this algorithm, it could potentially, insert some behavior that will change the result right there in between those two steps. So we want to disallow that in this algorithm. We want to kind of cheat in a way, but it's useful for this algorithm, and just say do those things simultaneously. So this is bubble sort. This is the part we wrote. This is the part that got generated. And there, as you can see, is that quote unquote hello world of TLA plus. You have your spec and you have your next. Okay, so what's next is we have the algorithm, but what do we want to check about it? What are some properties that we want to check? So let's express those. We really only had a few. Let's put some types on, just for sanity's sake. We wanted I to be in 1 to n. So this variable here, we want it to always be less than n. Okay, that looks good. J is the same. J in 1 to n. A in, and even though this is by definition, it just serves as documentation. I've also found that writing the type OK helps me make sure that this is what I really intend. So it's helping me kind of check my work. It's kind of like when you were in grade school and you did the division and then you did the multiplication the other way. It's like, well, of course it's going to work out because one's the opposite of the other. But it just helps you check your work and think things through. A0 in 1 to n, nat, and PC in label 1. Now, this one here is a little peculiar. I'm doing this because I'm going to make a refinement later, and I'm going to use the PC variable. Now, if you remember, we removed this simultaneous step, it ended up creating a new label. So this is also like, I'm defining the PC. I need the PC to have a particular behavior for my refinement to work out. So this is somewhat uncommon in specifications because the PC is this almost artificial thing that comes from the generated TLA+. But for the purposes of this demonstration, I want to constrain it just so that my refinement follows the way I expect it to. Okay. All right, so that's our type OK. And then what does a sorting algorithm do? It sorts things. So is completely sorted is defined as for all A and B. That white space wasn't significant. I like the space there. 1 to n, such that A is less than B implies A is less than or equal to A, B. Okay. So for every pair of integers, the index into A, if the index A is less than B, then the value of A at A is less than or equal to the value of B at B. So this is just defining ascending ordering. Okay. Computational complexity. Now, if you watched the abstract specification first, we didn't do computational complexity, and that's important. Here, we're implementing a particular algorithm that has a particular time complexity. It's big O of n squared. We want to check that for the input size that we defined. The abstract spec didn't have a particular time behavior or time complexity, so we don't specify it. Total specs is less than or equal to n times n. So n squared. Oops, not specs. Spaces. Thank you for checking my work. Okay. All right, that looks good. Sorted when done. So when the algorithm completes, we expect the PC to be equal to done, and that implies is completely sorted. There we go. So when the PC is done, that implies is completely sorted. Okay. That's it. Let's run our specification. So we're going to do a new model, bubble sort demo. Okay. And our model knows that we need a value here, so we're just going to do a small n for demonstration. We cannot sort over the infinite set of natural numbers, so we're going to define a size that we care about. So we are going to look up nat, and we are going to say nat maps to 1, 2, 3. So now the natural numbers is redefined as 1, 2, and 3. And again, this is just small so that the model runs quickly for demonstration. Okay. And then we're going to add our invariants. We have our type, okay. We have our sorted when done. And we have our, did I have that in their buffer? No, okay. Okay, computational complexity. And we want to check for termination. We want to check for termination because we really care if the thing does not deadlock. All right, let's run it. I typed this wrong. It is the sequence 1, 2, 3. Okay, put that back. There we go. It is the sequence 1, 2, 3, not the set 1, 2, 3. Okay, and let's run, not you. Let's run you. Okay, so we have our sorted specification. We have our bounded complexity. We can make n bigger. We can make the input set, the natural numbers, bigger. So we can now sort our stuff. So we have implemented bubble sort. And in the final part of this talk, we are going to define a refinement, and we're going to relate our interface with our implementation and show that the two work together, that they are cooperative.